Welcome. Uh, Today's lecture is about HVDC link control schemes. I will write here HVDC link control schemes. Actually, in HVDC link control schemes, we are going to discuss various techniques or various methods of generating the firing pulses for the operation of both the converters. The converter which is operating at the rectifier station and the converter which is operating at the inverting station. Okay, so we already know that a rectifier has following characteristics. If you see the control characteristics of the converter operating in rectification mode, it has CIA characteristic, it comprises of CC characteristic, and it comprises of VD call characteristic. Similarly, the other converter which is operating in inversion mode of operation comprises of following characteristics: CEA, C beta means constant beta characteristic, CC, and VD call. Now for getting these characteristics, you need to calculate alpha. Alpha means delay angle or firing angle. Okay. Now various schemes have been proposed in literature for generating the firing pulses or control pulses with a delay angle of alpha for both rectification operation as well as inversion operation. Now let us try to study what are the various firing control schemes or types of control schemes. Broadly, the control schemes which are proposed in the literature for the generation of control pulses are divided into two classes or two groups. One is called individual phase control scheme, individual phase control, which is also called IPC. And another type of control scheme for the generation of firing pulses or control pulses is called equidistant pulse control. Equidistant pulse control, EPC. Okay, let us discuss them one by one. First of all, we will discuss individual phase control technique, IPC technique. I should write IPC technique. In IPC technique, or in this scheme, the firing instance or the firing instant of each valve is determined individually. So I will write firing in this technique, in this control technique, the firing instant of each valve is determined individually. So that's why it's called individual phase control. Actually, depends upon the commutation voltage. I mean, you have to find the commutation voltage of each valve separately, and depending upon the commutation voltage, the delay angle or firing angle is calculated and firing pulses are issued. For example, if you see the examples, this may be the commutation voltage EAC, commutation voltage of valve 1. I will write here valve 1. Okay. Say for example, this may be the delay angle alpha, and similarly the commutation voltage of valve 3 is EBC. This is the commutation voltage of valve 3. So therefore you have 6 valves. Once you know the commutation voltage of the 6 valves, so your control logic circuit will then determine, or it will calculate alpha. Okay, you know how it calculates alpha. Some equations it solves and it calculates alpha, and once alpha is determined or alpha is calculated, firing pulses are issued to various valves. So therefore, since you have 6 valves, and 6 valves are fired individually depending upon their commutation voltages, so individual firing of 6 valves is done. So you need 6 parallel delay circuits. 6 parallel delay circuits are required. 6 parallel delay circuits are required. So each delay circuit corresponds to an individual valve. Okay, say for example value 1 you need one delay circuit, for value 2 you need another delay circuit, up to value 6. So you have 6 values in a 6 pulse converter, so you need 6 parallel delay circuits. Now this individual pulse control scheme is further classified into two techniques. IPC is further divided into two techniques. One is called linear firing scheme. I will write here linear firing scheme. Linear firing scheme, and another scheme is called inverse cosine firing scheme. Inverse cosine firing scheme. Let us discuss these firing schemes one by one. These are the two different variations or two different schemes which come under the category of individual phase control. Okay, IPC technique, linear firing scheme and inverse cosine firing scheme. Now, first of all, we will discuss linear firing scheme. Linear firing scheme. In linear firing scheme or in inverse cosine firing scheme, since 6 parallel delay circuits or firing circuits are required, I will show you one firing circuit or one delay circuit. This may be your 3-phase 6 pulse converter which is to be fired, and these are your 3 phases or 3 lines A, B and C. This is the output voltage of your converter VD, and the current is ID. Okay, fine. Now what we do, let us try to fire value 1 of your converter. What is the commutation voltage of value 1? EAB. So commutation voltage of value 1 is line voltage EAB. If I remember exactly, probably it is EAB. 5, 6, 5. No, it is EAC. EAC. Commutation voltage of value 1 is EAC. So this is, I put a voltage sensor across lines A and B. So the voltage sensor will read the line voltage EAC, which is the commutation voltage of value 1. Then I have a step down transformer. Okay, with the help of this step down transformer, I step down the voltage because my control logic circuit operates. It does not operate at very high voltages. It operates at very low voltages. Okay, of the order of a few volts. Then I have a zero crossing detector circuit here. ZCD means zero crossing detector circuit. Then the zero crossing detector circuit generates the zero crossing pulses, and the output of zero crossing detector circuit is given to delay circuit, or I should call this control logic circuit. Control logic circuit. CLC. CLC means control logic circuit. The other input to control logic circuit is control voltage, which is variable, VC. It's a DC voltage. Now, what is the output of control logic circuit? Output of control logic circuit is delay. These firing pulses. Now, firing pulses are not given to value 1 directly. They are given to value 1 through a driver circuit. This is your driver circuit. I hope you know what is the function of driver circuit. Whenever you use a low power control logic circuit, which may be an electronic circuit, digital electronic circuit, or which may be a microprocessor based circuit or digital signal processor, where a program is run and control pulses or firing pulses are generated, you need electrical isolation between control logic circuit and the power device, the valve. Okay, I hope you already know why we need electrical isolation, and you also need to amplify the amplitude of control pulses, because control pulses may be too weak to fire your SCR. So the function of driver circuit is it has two-pronged function. It provides electrical isolation and also pulse amplification. So therefore, if you see the driver circuit, this is pulse transformer, which provides pulse isolation. This is gate and this is cathode. So this is firing pulses. I will write here firing pulse to value 1. Okay, so this may be the firing pulse. So what is this? This is pulse transformer. What is the function of pulse transformer? The function of pulse transformer is to provide electrical isolation between control logic circuit and your device, okay, thyristor. And other function of driver circuit, the other function of driver circuit is pulse amplification. So amplification is done by driver circuit, and the pulse transformer, which is of course part of driver circuit, provides electrical isolation. So therefore you generate the firing pulse for value 1. So this is one delay circuit. So you need 6 such delay circuits for 6 valves. And for the operation of this control logic circuit, which may be an electronic circuit or digital circuit, and similarly the zero crossing detector, you need a power supply. So what is done? You have another transformer here, another step down transformer. This step down transformer gives supply to a rectifier, and then this is the power supply VDC, which is given. This power supply is given to this electronic circuit, that is the zero crossing detection circuit, and also to control logic circuit, and also to driver circuit, right? So this is the power supply. I mean, there may be other components of power supply also. I am not showing. Maybe there is a filter capacitor also, but I am showing a simple diode rectifier based AC to DC rectifier, which creates power supply. Okay, now the operation is very simple. Why this scheme is called linear firing scheme, you will try to understand it with the help of following waveforms. What is the output of this transformer? It is a step down transformer. Let us call this output of this transformer, that is transformer secondary voltage, step down voltage, as Vs. So this is the step down voltage of transformer. So these are zero crossing points, 0, pi, 2 pi, 3 pi, and so on, right? Now what is the function of this what we call as zero crossing detection circuit? Zero crossing detection circuit is an electronic circuit, a digital circuit, which generates sharp pulses at the zero crossings. I mean, your first zero crossing is at here. This is the positive going zero crossing. So it generates a sharp pulse at the zero crossing. Next zero crossing is at pi. So your zero crossing detector circuit generates another pulse here, which is called zero crossing pulse. Another sharp pulse at 2 pi. This is also zero crossing pulse. Another zero crossing pulse here, and so on. So this is I will write here zero crossing pulses. These are not firing pulses. These are zero crossing pulses. So a sharp pulse is generated by zero crossing detection circuit, each at these zero crossing points, 0, pi, 2 pi, 3 pi, and you can see like this. Now this output of zero crossing detector, that is the zero crossing pulses, when they go to control logic circuit again comprises of discrete electronic circuit or digital electronic circuit, which generates a sawtooth voltage. Okay, I will not go into the details of this electronic circuit. You can find these the details of these electronic circuits from the literature. So when first zero crossing pulse is given to this control logic circuit, what this control logic circuit does, it has a sawtooth generator. So the sawtooth generator generates a sawtooth wave, voltage wave, from first zero crossing pulse to next zero crossing pulse, like this. This is the sawtooth voltage wave, or this is also called ramp voltage. Okay, let us call this VSW. SW means sawtooth voltage. Then here is next zero crossing pulse. As soon as this next zero crossing pulse comes, another sawtooth wave is generated. Then another zero crossing, another sawtooth wave is generated, and then at each zero crossing you get a sawtooth voltage. Then within this control logic circuit you have a comparator. Okay, you have a comparator which is part of this comparator. Now comparator has two inputs. It has DC control voltage, which is variable, and it has sawtooth voltage. So it does the comparison of the two. Okay, now sawtooth voltage is one input to your comparator. It's minus, and VC is another. I mean, it's an amplifier, non-inverting amplifier. What is the first input to this non-inverting amplifier? VC, control voltage. And another signal at inverting terminal is this sawtooth voltage, which is generated by this control logic circuit like this. Okay, then it does the comparison between the two. The question is this control voltage, how do you generate this control voltage? Control voltage is very easily generated. You know, your aim, I mean, if you are trying to control the converter, the delay angle of the converter operating in the rectification mode and in rectification station, then alpha has to be controlled. I mean, the aim is to maintain the DC line current as constant. So in that case, this is ID reference DC line current, and this is actual DC line current, transmission line current. It is sensed by a current sensor, and then the comparison is done here. And if ID is not equal to ID ref, an error is generated, and that error is given to PI current controller. CC means current controller, and this output of this PI current controller is VC, control voltage, and that control voltage goes as input to the comparator here. Comparator is basically, it's a part of control logic circuit. I mean, that is embedded within this. I am showing that separately. I mean, it is like this. So this control voltage, VC, it is a DC voltage. It may vary from 0 to 5 volts or 0 to 12 volts. It depends. Okay. So how do you generate this control voltage? Like this. ID, that is DC line current, transmission line current, is compared with reference current. Our aim of the controller is to maintain the DC line current constant, so that it gives constant current operation. If ID is not equal to ID ref, an error E is generated. That error is processed by PI current controller. This is PI current controller. CC means current controller. The output of this PI current controller is a DC voltage VC. It's variable voltage. It varies from 0 to 5 volts or 0 to 15 volts. And then this VC goes as input to this comparator. This is your comparator. I will write here comparator, which is part of your control logic circuit. The other input to comparator is the sawtooth wave, which is generated by this zero crossing detector and control logic circuit. Zero crossing detector, at each zero crossing generates a zero crossing pulse, and when that zero crossing pulse goes to control logic circuit, there is an electronic circuit which generates the sawtooth wave like this. Then the two waves are compared here in the comparator. The logic is that at the point of intersection of VC and this sawtooth wave, firing pulse is generated. Suppose this is your VSW, sawtooth voltage, and suppose this is VC. This is VC. So you have two voltages. You have this sawtooth voltage and you have this VC. The comparison takes place here. I mean, the two waves intersect here. So at this instant, you get the firing pulse, first firing pulse you get here. And you get that firing pulse after a delay of alpha electrical degrees. The second firing pulse you get in the negative half cycle of source voltage at this point of intersection. This is the job of comparator. The comparator generates the firing pulses at the points of intersection of VC and VSW, because the two inputs to comparator are VC and VSW, sawtooth voltage and DC control voltage. The third control pulse is generated here, and so on. I mean, if this is alpha, what is this? This is pi plus alpha. This is 2 pi plus alpha, 3 pi plus alpha, and so on. This is the generation of firing pulses. Now, if the amplitude of VC is decreased, I mean, now you see, if I decrease the amplitude of VC, control voltage, because this control voltage is variable, it depends upon the error. I mean, depending upon the error, if VC decreases, VC comes down, it decreases, then the point of intersection is here. So in that case, what is alpha? Alpha is reduced, alpha decrease ho jata hai, delay angle reduces. Now, if on the other hand, the error is such that the VC increases, so what happens? VC increases. And if VC increases, the point of intersection is shifted. So your alpha also shifts. So you have large alpha. So if VC goes up, alpha increases. If VC goes down, alpha decreases. So that means alpha, that is delay angle, is directly proportional to control voltage. You can see as control voltage increases, alpha also increases. As control voltage decreases, alpha decreases. Okay, since VC varies directly with alpha varies directly with control voltage. That's why this firing scheme is called linear firing scheme. Now, we can say as control voltage increases or decreases, delay angle or firing angle also increases or decreases. Okay, so delay angle is directly proportional to control voltage. So which means alpha is directly proportional to control voltage. If you find alpha, alpha is equal to KVC, where K is the constant of proportionality. Now we know that converter average output voltage, VD, is equal to 3 root 3 EM by pi cos alpha. Or we know VD is equal to VD naught cos alpha, where VD naught is 3 root 3 M by pi. So VD is equal to VD naught cos alpha. What is alpha? Alpha is K into C. So therefore, that means VD is directly proportional to, VD naught is constant, it's directly proportional to cos of C. This is K into VC, control voltage. So this is directly proportional to cos of VC. Okay, so therefore as VC increases, cos VC decreases, so average output voltage decreases. That is clear from waveforms also. You have seen as VC increases, alpha increases, and as alpha increases, average output voltage decreases. And similarly, as VC decreases, alpha also decreases, and decrease in alpha means more average output voltage. So therefore, in terms of VC, control voltage, VD is directly proportional to cos of VC. Okay, as VC increases, average output voltage decreases. As VC decreases, average output voltage increases. So this is about linear firing scheme. Now, the problem in this linear firing scheme is that you need the detection of zero crossings. Zero crossing detection is one of the requirements. I mean, why do you need to detect zero crossings? Okay, because your ramp voltage is generated from 0 to pi, then from pi to 2 pi, 2 pi to 3 pi, 3 pi to 4 pi. At each zero crossing, 0, pi, 2 pi, your ramp starts rising. Then say from first zero crossing to second zero crossing, it rises, then it comes down. From second zero crossing to third zero crossing, it rises and comes down, and so on. So therefore, this type of ramp voltage waveform makes your control pulses or firing pulses synchronized with zero crossings. So I will write here sawtooth voltage, SW voltage, which is generated because of zero crossing pulses. I mean, which is because of zero crossing pulses. Okay, synchronizes the occurrence of firing pulses with zero crossings. I mean, when I say alpha is say 40 degrees or 50 degrees, it is 50 degrees right from zero crossing 0. And if I say it is here pi plus alpha, pi plus 50 degrees, pi is zero crossing. So you always measure firing angle or delay angle from zero crossing. So that means when I say firing pulse is generated here after a delay of alpha maybe say 60 degrees, 70 degrees, you measure 60 degrees from zero crossing. So that means this firing pulse is synchronized with its zero crossing, and that is possible only when you detect these zero crossings. And because of detection of these zero crossings by this zero crossing detector, because of generation of these zero crossing pulses, this sawtooth voltage is generated, and this sawtooth voltage and VC comparison gives us firing pulses, and these firing pulses are synchronized with zero crossing. So therefore, zero crossing detection is one of the main requirements of linear firing circuit. So that was about linear firing scheme. The second type of firing scheme, which comes under IPC, that's individual phase control, is inverse cosine firing scheme. I will quickly discuss with you inverse cosine firing scheme. Let me first of all draw the schematic diagram of inverse cosine firing scheme. The schematic diagram is simple. It is like this. So first of all, you sense the supply voltage, source voltage. I will write here sensed sine wave. You sense the sine wave voltage with the help of a voltage sensor. Then you use a phase shifting network. Okay, I use a phase shifting network. This is a phase shifting circuit or phase shifting network. What will this phase shifting circuit do? It will convert your sine wave into cosine wave. So you get cosine wave. Now this cosine wave goes as an input to the comparator, second input I mean, this is your cosine wave. It goes as an input to comparator. The other input to comparator is control voltage, VC. And at the output of inverter, at the output of this comparator, you get firing pulses as usual. Now, how do you generate this VC? Same way, you have the idea is to maintain this DC line current constant. That is, ID should be equal to ID ref. If there is any error, whenever there is any error, that error is processed in a PI current controller. This is your PI current controller, proportional integral current controller. The output of proportional integral PI current controller is control voltage VC, and that is one of the inputs to this comparator. Another input to comparator is your cosine wave. Okay, and then how the control pulses are generated? Let me show you the generation of control pulses. Your sensed sine wave is like this. This is your sensed sine wave, for example. 0, pi, 2 pi. Now, what will your phase shifting network do? It will convert, or it will transform this sine wave into cosine wave. That's the job of phase shifting network. Okay, so it transforms it into cosine wave. Let us call this cosine wave as VR. R means reference wave. So this is your cosine wave. When sine wave is at 0, cos wave is at peak. When sine wave is at peak, cos wave is at 0. This is the cosine wave. So this is how, this is generated. Okay. Now, this is your cosine wave. Let us call this cosine wave as VR. I mean, I have a small pulse here and I have a small pulse here also. I will explain later on what is the function of these pulses. This is your cosine wave. This is it. Now, this cosine wave, as you can see, it is compared with DC control voltage, which is generated by this circuit. This is your DC control voltage, VC, which is variable. I mean, if this is your VR, you have another VR. Negative of VR is also there, like this. This is minus VR, minus VR. Then the comparison takes place like this. Okay, the first comparison takes place somewhere here. The comparison between the two gives firing pulse. So these are firing pulses, control pulses. First control pulse is after a delay of alpha. Second control pulse is somewhere, say here. Here is second control pulse. This is pi plus alpha. Third control pulse is here. Okay. So this is the occurrence. This is the occurrence of firing pulses. First firing pulse is at this point of intersection. Second firing pulse is here. Third firing pulse is here, and so on. So this is the occurrence of firing pulses. Now, this is this and this. They are called end stop pulses. They are called end stop pulses. End stop pulses. I will explain what this end stop pulse is. Now this is VR and this is VC, control voltage. Now let's call this point as point P. At point P, VR is equal to VC. VR is your cosine wave, and this VR is given as VRM cos alpha, because this is cosine wave. Okay, so therefore at point P, VC is equal to VR, therefore VC is equal to VR, VR is VRM cos alpha. Okay, so from this we can find cos alpha is equal to VC by VRM. What is VC? VC is the control voltage. It is fixed in amplitude for a given value. VRM is peak of this cosine wave. It's also fixed. So therefore alpha is equal to cos inverse VC by VRM. Now, as far as this VRM is concerned, VRM is peak of this cosine wave. It's constant, but VC is not constant. VC is variable. Now, VC will be determined by this circuit. Depending upon this error, this VC may sometimes increase or it may decrease. So that means alpha is directly proportional to cosine inverse of VC. If you remember in linear firing scheme, alpha was directly proportional to VC. But in this inverse cosine firing scheme, alpha is not directly proportional to VC. It is directly proportional to inverse cosine of control voltage, VC. So since delay angle or firing angle is proportional to inverse cosine of control voltage, that's why this scheme is called inverse cosine firing scheme. That's why it's called inverse cosine firing scheme. In linear firing scheme, if you remember, alpha was directly proportional to VC. That's why that's called linear firing scheme. But here alpha is proportional to cos inverse of VC. That's why it's called inverse cosine firing scheme. Now I can write, now we know VC is equal to VRM cos alpha, or cos alpha is equal to VC by VRM. Let's call this equation as equation 1. Also, converter average output voltage. Converter average output voltage. We already know expression for converter average output voltage. VD is equal to VD naught cos alpha. So from this also you can find expression for cos alpha, that is equal to VD by VD naught. That's equation 2. So from equations 1 and 2, from equations 1 and 2, left hand side is equal to right, the left hand sides are equal, cos alpha, so right hand sides are also equal. That is VC by VRM is equal to VD by VD naught. So from this we can find VD is equal to VD naught by VRM into VC. Now what is VD naught? VD naught is peak of the voltage. VD naught is 3 root 3 em by pi. VD is equal to VD naught cos alpha. If you remember, this VD naught is equal to 3 root 3 em by pi. For given source voltage, it's fixed. And what is VRM? VRM is peak of the cosine wave. This is also fixed. So therefore, we can say VD is equal to KVC. So therefore, there is a linear relationship between average output voltage of converter and control voltage. That is, VD is directly proportional to VC. So therefore, if you plot, this is control voltage VC and this is VD. For control voltage equal to 0, output is 0, then as you increase control voltage, average output voltage also increases. This is VC, VRM, and this is the maximum average output voltage, VD naught. So this is the relationship between these two. Okay. So that is about inverse cosine firing scheme. So there are two different variations of individual phase control scheme. One is linear firing scheme and another is inverse cosine firing scheme. In linear firing scheme, zero crossing detection of pulses is there. I mean, zero crossing detection circuit is there, and control pulses are synchronized with the occurrence of zero crossings. So zero crossing detector is an integral part of linear firing scheme, and alpha is directly proportional to control voltage. That's why that scheme is called linear firing scheme. But in inverse cosine firing scheme, alpha is proportional to cosine inverse of control voltage. That's why it's called inverse cosine firing scheme. Now, these are two different variations of IPC. What are the drawbacks? Drawbacks of IPC, that is individual phase control scheme. We have discussed two types of individual phase control scheme, linear firing scheme and inverse cosine firing scheme. But it suffers from some serious drawbacks. Number one is, if due to some voltage distortion, zero crossing shifts, alpha also changes. I mean, you have seen that these schemes depend upon the detection of zero crossings. If the voltage is not purely sinusoidal, the sensed voltage, the voltage which you are sensing, I mean, this is the sensed voltage. If this is not sinusoidal, if this is non-sinusoidal, the zero crossing, instead of here, it may occur somewhere here because of distortion in the voltage. And because of, zero crossing shifts, because of the distorted voltage, the zero crossing may shift. So alpha will be calculated wrongly. So alpha will change. And therefore, your converter will, in addition to characteristic harmonics, the currents will have uncharacteristic or non-characteristic harmonics. So this will result in non or uncharacteristic harmonics. Uncharacteristic harmonics. Otherwise, in currents, there are characteristic harmonics only. So this will result in uncharacteristic harmonics in addition to characteristic harmonics. So characteristic harmonics are already there. I hope you know what are characteristic harmonics. Characteristic harmonics in current are given by Np plus minus 1, where P is the pulse number and N is an integer. Like for 6 pulse converter, the harmonics which are present in the current drawn by the converter are 5th, 7th, 11th, 13th, and so on. For 12 pulse converter, the most predominant harmonic is 11th, then 13th, then 17th, then 19th, and so on. Those are called characteristic harmonics. But if zero crossing shifts, alpha changes, then in addition to characteristic harmonics, there will be uncharacteristic harmonics also. This is first problem. Second problem is harmonic instability is caused. Harmonic instability is caused at frequencies where filter impedances and system impedances go in parallel resonance or are in parallel resonance. I mean, because of shifting of the zero crossing, there may be uncharacteristic harmonics, and because of this uncharacteristic harmonics and other type of harmonics, at certain harmonic frequencies, your filter, since you are already using filters, the filter impedance may fall in parallel resonance with the system impedance. System impedance, that means the source line impedance, and filter impedance may go in parallel resonance. And parallel resonance means that instead of suppressing the harmonic of that particular frequency, the harmonic of that frequency will get amplified. Okay, so this is another problem. This is called harmonic instability. Third problem is that you need additional harmonic filters. I will write here additional harmonic filters are required. Okay, because I already told you if zero crossing shifts, then in addition to characteristic harmonics, there may be uncharacteristic harmonics also. So you need additional harmonic filters. So because of these drawbacks, IPC scheme is not very popular in HVDC converters. So IPC scheme is seldom used for control of HVDC link. So therefore, what type of scheme is used for the control of HVDC link? The second type of control scheme, which is called equidistant pulse control. Now let us now discuss that. Second type of firing scheme or control scheme is called equidistant pulse control. EPC. Equidistant pulse control is very interesting, and it is very simple. In equidistant pulse control, what is done that no synchronization of control pulses with AC system is required. So because in IPC you have seen that since pulse generation is synchronized with the zero crossings, your pulses should be synchronized with AC system zero crossings, and if the voltages are distorted, zero crossing shifting is there, alpha changes, uncharacteristic harmonics will be there, you need additional filters and all that. Okay, so in equidistant pulse control, so I will write here in EPC technique, the main advantage is that no synchronization of control pulses or firing pulses with AC system. Within brackets I will write zero crossings. is required. I mean, you don't need to synchronize your firing pulses with zero crossings, or you don't need to synchronize your firing pulses or control pulses with AC system. And in this case, what is done, let alpha 1 be 5 degrees. For example, you have, this is the firing sequence, 6 1 1 2 2 3 3 4 4 5 5 6, and then again 6 1. Here value 1 is fired after 60 degrees, value 2 is fired after another 60 degrees, value 3 is fired, then after another 60 degrees, value 4 is fired, after 60 degrees, value 5 is fired, after another 60 degrees, value 6 is fired, and then cycle repeats. Let alpha 1 be 5 degrees. Therefore, what will be alpha 2? That is control pulse per second. For value 1, if alpha is 5 degrees, for value 2, what will be alpha? 60 plus 5. 60 degrees plus 5 degrees. That is 65 degrees. For value 3, what will be it? It will be 65 degrees plus 60 degrees. That is 125 degrees, and so on. So that means the calculation is done by your controller, and calculation is very simple. You need to know only the first firing or delay angle. Once you know the delay angle of value 1, then you just go on adding 60 degrees each to the firing of other values. Alpha 2, that is the value 2 will be fired after a delay of alpha 2, that's 65 degrees. Value 3 will be fired after 65 plus 60, that's 125 degrees. Value 4 will be fired after 125 plus 60, that's 185 degrees, and so on. So control is very simple, okay? And it is used for weak AC systems also. So I will write here, it produces pulses, that is control pulses or firing pulses, at equal intervals of 1 by fp, where p is the pulse number, f is the frequency, okay? Because we know that omega t is equal to 2 pi by p, okay? So from this, the time is given by 2 pi by omega p, and that is equal to 2 pi by omega. What is omega? Omega is 2 pi f into p. 2 pi and 2 pi goes, so that means the time is 1 by fp seconds. So after every 1 by fp seconds, firing pulse is generated. So it has got, this scheme has, although it is very simple and it does not need zero crossing detection, and hence all the drawbacks which are there with individual phase control IPC scheme, like linear firing scheme or inverse cosine firing scheme, all those drawbacks are overcome because you don't need zero crossing detection here. But this also suffers from some drawback. The drawback is, for example, if this is your generator, the generator, let us consider a thermal power plant. This is a high pressure turbine. This is intermediate pressure turbine, and this is low pressure turbine. The shaft of generator is coupled with the turbine, okay? Let us suppose this is the natural frequency of oscillation of high frequency turbine. F1, F2 is the frequency of oscillation of IP, and F3 is the frequency of oscillation of this LP, low pressure turbine, okay? Now this F1, F2 and F3, they are all subsynchronous frequencies. Subsynchronous frequency means less than 50 Hz frequencies. So what is the problem is that if harmonics from HVDC system enter the AC system, I mean your converter, your generator, generates the supply, and then you have an HVDC converter here, say rectification, the converter operating in rectification mode, okay? So you have a converter here. Okay, the problem through converter transformer, this is given to your HVDC system. Now this HVDC system generates harmonics in the currents, and if these harmonics from HVDC system enter the AC system, of course they will enter this AC system, okay? And then torque pulsations in this generator will be produced, and because of torque pulsations in the generator at frequencies F1, F2 and F3, which are subsynchronous frequencies, the torque pulsations in the generator will, because of the harmonics in the current. Say your HVDC converter operates at a certain delay angle alpha, and it generates the harmonics in the line currents. All the three line currents, IA, IB, IC, they are rich in harmonics, and these harmonics enter the AC system. They enter the generator windings. So your generator windings are not carrying the sinusoidal currents, they are carrying non-sinusoidal currents. And the problem is that because of these currents, harmonic currents in the generator windings, torque pulsations at subsynchronous frequencies, that's frequencies F1, F2, F3, which are less than 50 Hz, are produced. And if these torque pulsations at these frequencies, they result in torsional oscillations of high amplitude in the turbine. This may be your turbine shafts also vibrate at certain natural frequency. If the torque pulsation of generator because of harmonic currents matches with these natural oscillation of these natural frequency of oscillation of this turbine shaft, then the oscillations which are called torsional oscillations of very high amplitude are produced in generator and that may result in instant damage of the turbine shaft. So turbine shafts, because of torsional oscillations, will get damaged. So this is the problem with this equidistant pulse control scheme, EPC scheme. But there are some methods have been already suggested in the literature whereby these torsional oscillation amplitude can be limited, and your turbine shaft and generator shaft can be protected. So therefore, we can say the drawback of EPC is that EPC scheme, that is equidistant pulse control scheme, produces negative damping contribution to torsional oscillations. I mean, they may result in high amplitude torsional oscillations here, which may cause damage to the turbine shaft and also generator shaft. But this is not a serious drawback. This drawback can be overcome. Now, just like in IPC, you have two schemes. You have linear firing scheme and inverse cosine firing scheme. In EPC also comprises of two schemes. See, if you see equidistant pulse control scheme, it comprises of two. It is broadly divided into two types. One is called pulse frequency control scheme, pulse frequency control, PFC. And another is called pulse phase control, PPC. Pulse phase control, PPC. Okay, let us discuss briefly. So first of all, we will discuss pulse frequency control scheme, PFC scheme. I will just draw the schematic diagram or block diagram and try to briefly explain that. This is integral dt from Tn-1 to Tn. This is control voltage Vc plus this is V1. V1 is called bias voltage. Vc is control voltage, and integration is done here in this block, and then this goes to output of integrator goes to comparator. We have a comparator here, and output of comparator goes to pulse generator. You have a pulse generator here. Other output of pulse generator, which is called V3, goes as second input to comparator. And pulse generator generates the firing pulses after a delay of alpha, but those firing pulses have to be decoded. So you need a ring counter. You need a digital counter here, and this digital counter will generate the firing pulse after a delay of alpha electrical degrees. Now this circuit from here to here, this is called voltage controlled oscillator, VCO. VCO is called voltage controlled oscillator. Voltage controlled oscillator. Okay, now V1 is bias voltage and Vc is control voltage. And you already know how to generate this VC. VC is generated by the closed loop control scheme, where ID has to be made equal to ID ref. If ID is not equal to ID ref, an error is produced, which is processed by PI controller, and VC is generated. It's a control voltage. But here we use bias voltage also. Why this bias voltage is used, I will come to that after some time. Let me first of all try to explain it with the help of a simple diagram. This is time axis. Our control pulses are generated like this. Sawtooth voltage again is generated here, sawtooth voltage, but it is not based on zero crossing detection. Okay, this is T by 6. This is here T by 6 time interval, T by 6, and that is also called V3, voltage amplitude V3. Now here this is VC. Here I can say VC is equal to 0. There is no error between, VC equal to 0 means, if this is ID ref, reference DC line current, and this is actual DC line current, error is produced here. And that error is given to a PI current controller, and you get VC. If there is no error, if ID is exactly equal to ID ref, error is 0. So for error, in that case, error is 0 means control voltage is also 0. No control action. Let us suppose due to some reason ID has, ID is not equal to ID ref. So now error will be produced, which will be processed by this PI current controller, and PI current controller will give some VC, control voltage. Let us suppose some control voltage is produced here. This is control voltage. It is produced and then it becomes 0 again. This is control voltage due to error between ID and ID ref. And now firing pulses or control pulses will be generated like this. First control pulse will be generated here. After a delay of say alpha electrical degrees, next control pulse will be generated. And next control pulse, instead of getting generated here, it is delayed. Its generation is delayed because control voltage has increased due to error between ID and ID ref. And your next firing pulse is not here, it is somewhere here. And after some time, when error is again equal to 0, when VC is again equal to 0, normal sequence of firing takes place like this. Okay. Now, as far as this is concerned, let me explain this part. So, what will integrator do? It will integrate from Tn minus 1 to Tn Vc plus V1 dt, and that is equal to V3. Now you can see this is your this is Vc. You can see this is Vc, this is V1. Vc plus V1 is integrated by this, and this should be exactly equal to this V3. So this should be equal to V3. That's what I am writing here. K1 times integration of Vc plus V1 dt is equal to V3. So from this I will get K1 Vc plus V1 is equal to V3 if you integrate this, divided by Tn minus 1. This is called pulse duration. This is pulse duration. And this is equal to V3 P F0. Okay. What is 1 by Tn minus 1? It is 1 by P F0. Okay. You have already seen that. That is this. What is the time of pulses? That is 1 by Fp. You have already written that here. So therefore K1 into this is equal to this. Now I will write at steady state. At steady state, control voltage equal to 0. Therefore, what is K1? K1, if control voltage Vc is equal to 0, so K1 into V1 is equal to V3 divided V3 P F0. K1 V1, because here Vc is equal to 0, is equal to V3 P F0. So from this you will get K1 is equal to V3 P F0 by V1. So the question is why we need this bias voltage here. You would have put a question here. If control voltage is there, why do you need bias voltage? This bias voltage V1 is required because if from this equation, if V1 is equal to 0, so what is your K1? K1 will be infinite and your controller will become unstable. Controller will become unstable. That's clearly shown from this equation. So therefore you need some bias voltage, positive bias voltage, which will not make K1 infinite and which will keep controller stable. Otherwise, if V1 is not there, bias voltage is not there, that is V1 is equal to 0, K1, that's this gain will be infinite and that will render your controller unstable. So that is the significance of bias voltage. That is why with control voltage we add some small positive bias voltage here, V1. This is the significance of V1. Now the drawback of this scheme is that if you write the drawback, frequency change is not taken into consideration. Frequency change is not taken into consideration. Because if you see from this equation, frequency is F0, it is constant. I mean, if supply voltage frequency changes, say from 50 Hertz, it changes to 50.5 Hertz or 51 Hertz. That is not taken care of by this scheme. So therefore, the control pulses are not generated at proper places or after proper, time, after appropriate time. So there may be, delay or some control pulse may get issued after a delay or maybe early issuance of control pulses will be there. This problem, however, has been solved by an engineer in the name of Ainsworth. So Ainsworth suggested, so I have written here, Ainsworth suggested frequency correction control as. So what he did, he said that instead of integrating Vc plus V1, you just integrate V1 dt is equal to V3 plus Vc. I mean, from this, what is K1? K1 is equal to V3P F0 by V1. So therefore, our control logic scheme will get modified like this. We are not integrating Vc plus V1. See, here you were adding Vc and V1 and then integrator was integrating this. This is what you have done here. Vc plus V1, it was integrated from Tn minus 1 to, instead of integrating Vc plus V1, only V1 is integrated from Tn minus 1 to Tn dt. Then its output is given to comparator and another input to comparator is given like this. This is the other input to comparator, Vc and V3. Vc plus V3 is another input and then it goes to pulse generator. So what this does, this, in this case, the dependence on frequency is not there. I mean, if frequency of the supply changes, that is automatically taken care of by this control scheme, okay? And then it has a better stability. So that was about pulse phase control, pulse frequency control. The second type is pulse phase control. Pulse phase control, PPC. So in this control scheme, a train of pulses, I would like to say a train of pulses generated proportional to the control voltage. A train of control pulses or firing pulses. A train of control or firing pulses is generated proportional to control voltage, Vc. Okay, so the diagram is like this. As usual, you have an integrator, K1 integration, and then input to this is called current order. and this is V1, that is bias voltage. And then this goes to comparator. This is comparator. The other input to comparator is V3, and then this is your pulse generator. Pulse generator, it generates the control pulses after a delay of alpha electrical degrees. The output of pulse generator is given to this integrator DT. Okay, so this is your voltage controlled oscillator, VCO. Voltage controlled this is the voltage controlled oscillator, VCO. So the working is like this. It's simple working. Let us suppose initially this is the generation of this ramp signal, 3, 4. Let us suppose after this 4 control voltage increases. So what will happen? This also will increase. Okay, and then firing pulses will be like this. This is time axis, this is time axis. What is this? This is control voltage, VC. Okay, this is control voltage. This is integrator output. I will write here integrator output. When control voltage is low, this is the integrator output. When control voltage increases because of error between ID and IDRF, this changes its position. So the firing pulses are generated like this. First firing pulse is generated here. Next firing pulse is generated after a delay of 60 degrees. Next firing pulse is generated after another delay of 60 degrees. Next firing pulse here after. The next firing pulse could have been generated here after another 60 degrees. But since control voltage has gone up, instead of generating firing pulse here, it will generate, instead of generating firing pulse here, it will generate firing pulse here. And then the 60 degree is maintained. 60 degrees, 60 degrees. Okay, so this is how it works. So this was about various control schemes. We have broadly discussed individual phase control scheme, IPC scheme, and then equidistant pulse control scheme, EPC scheme. In IPC scheme comprised of 2 schemes, linear firing scheme and inverse cosine firing scheme. Both are based on detection of zero crossing, and because of if there are some distortions in the voltage, zero crossing shifts, and firing pulses are not properly generated at right moments, and that results in addition to characteristic harmonics, non-characteristic harmonics also. So those problems are solved in equidistant pulse control scheme, EPC scheme. And EPC scheme was further classified into pulse frequency control scheme, PFC scheme, and pulse position control scheme, PPC scheme. And in both the schemes we have seen that there is no need to detect the zero crossings. Zero crossing detection is not required at all. So all the problems which are there because of detection of zero crossings, those problems are overcome. And to end my today's lecture and to end this module, let me now show you the block diagram. Like I will show the block diagram. I will write here complete basic control scheme of HVDC converters. Let me show you the complete basic control scheme of HVDC converters. So your HVDC converters, one converter is here. This may be operating in the rectification mode. And this is LD. This is line current ID. This is line resistance R. Then this is VD. And this is again LD. I'm dividing this DC line reactance into 2 equal parts. And this is another converter which may be operating in the inversion mode. Okay. This is the converter transformer, tap changing converter transformer. This is AC bus. It is fed from the AC bus. This is transformer tap changing control, TCC. This is, I will write here, transformer tap changer control, TCC control, TCC. And it is based on alpha RF and alpha. The error goes here if alpha is not equal to reference alpha, then error goes here, and transformer tap changer control gives input to this transformer tap changer, which may be a servo stabilizer based tap changer, and tappings of this transformer are changed. Either you go to upper tap or you go to lower tap. Okay, similarly on this side you have another, converter transformer with tap change. This is AC bus, as usual, AC bus here. This is the transformer tap changer control. Okay, now this TCC, transformer tap changer, depends upon this. So it is minus, this is plus R into ID. R is this, R into ID means voltage drop here, and this is, we need a reference voltage of the converter V0. If there is an error between the three signals, and it goes to transformer tap changer, and transformer tap changer operates. And regarding the electron, this is the electromechanical control, tap changer control. What about this electronic control? Electronic control is like this. It's very interesting to see. This is your, let me first of all draw, and then I will explain. See, what we do is that this VD is given to this block, VD. It is given to VD call also. We from system control, we find what is the power in the HVDC link. And since HVDC voltage is sensed, that then in this block, this power is divided by voltage. The power in the HVDC link is divided by the HVDC link voltage. That gives us HVDC current ID, and that is given to voltage dependent current or a limit, because under very low voltage conditions you already know that current limit has to be set, and that is set by this VD call. And then this gives your ID ref. This is ID ref, reference DC line current, and this is a current sensor. This is current sensor. Whatever current is flowing in this DC link, this is the current flowing in DC link that is sensed by this current sensor, and this is the actual sensed current. Now, if the actual line current is not equal to this reference line current or reference DC current, then it goes to current control amplifier. CCA means current control amplifier. This signal may be very weak, it needs to be amplified, so it goes to current control amplifier. And after current control amplifier, it goes to firing control circuit. Okay, and firing control circuit you have already studied. It may be IPC or it may be EPC. Generally it is equidistant pulse control based scheme. Okay, it goes to this and it generates the firing pulses after a delay of alpha electrical degrees, and this converter is operated. What about this converter, which is operating in the inversion mode of operation? Here also you have VD call. This is VD call. It receives input VD and it receives current ID or I1. Then its output is ID dash. It goes to plus, and this is minus. This is minus ID. This is ID ref, and this is ID. Okay. And then as usual this goes to current control amplifier, and after current control amplifier it goes to firing control circuit, FC. and firing pulses are generated here after a delay of alpha electrical degrees. Okay, so this is your rectifier, this is the inverter. So this gives complete basic control structure of HVDC converters. Your HVDC converter control comprises of electronic control, which is this, where the converter, this which is operating in rectification mode, or this converter which is operating in inversion mode, where it is operated electronically. I mean, for this rectifier, you have to generate reference current IDREF that has to be compared with the actual DC line current. Any error after amplification is given to firing circuit. Okay, FC means firing circuit. And what is the function of this firing circuit? We have already discussed various types of firing circuits to generate the firing pulses at a particular delay angle, so that ID becomes equal to IDREF. Similarly, for inverter, this converter which is operating in inversion mode of operation, this is how control is achieved, electronic control. VD call in both blocks, here as well as here, VD call are, it's incorporated. And in addition to this, you have seen in one of the previous lectures, if electronic control fails to make your ID equal to IDREF, then tap changing transformers have to operate. This is the tap changing control of rectifier transformer, and this is the tap changing control of inverter transformer. So this completes our discussions on various control schemes, the control characteristics and control schemes of HVDC link. Over the last 3 to 4 lectures, we have studied various control schemes of HVDC link, control characteristics, simplified control. We started with simplified. In fact, we started our lecture with desirable control features. After understanding what should be the desirable control features, we tried to draw control characteristics for both converter operating in rectification mode and another converter operating in inversion mode. And then we kept on refining those characteristics with further modifications. And finally, at the end of second lecture, we developed the complete control characteristics of an HVDC control link. And I have already told you that those characteristics comprise of a rectifier for rectification converter, CIA, CC, VD call; for inversion converter, CEA, C beta, CC, and VD call. And then in today's lecture, we discussed various types of control schemes, firing schemes, and we broadly divided those firing schemes into individual phase control, IPC control scheme, and equidistant pulse control, EPC control scheme. IPC technique was further divided into linear firing scheme and inverse cosine firing scheme, and we found that both linear firing scheme as well as inverse cosine firing scheme, although they are simple in operation, but they suffer from the drawback because they depend upon the detection of zero crossings, which has following drawbacks, like if due to some voltage distortion zero crossing shifts, alpha also changes. This will result in uncharacteristic harmonics in addition to characteristic harmonics. And second is harmonic stability, and third is additional harmonic filters are required. To overcome this drawback, the other firing scheme or control scheme is equidistant pulse control, EPC scheme. And this EPC scheme is very simple. It does not depend upon the detection of zero crossings, and it was further divided into pulse frequency control, PFC, and pulse phase control. And we have tried to understand briefly both the schemes, and we have found that these schemes are simple. They depend upon the generation of control pulses at equal intervals. If alpha 1 is 5 degrees, alpha 2 will be 60 plus 5, that's 65 degrees. Alpha 3 will be 65 plus 60, that is 125 degrees, and so on. And and then we try to understand complete basic control scheme of HVDC link. So this completes our discussions on module 4, and this marks the end of your module 4. Now we are left with last module, module number 5. I will take a break of 2 to 3 days for getting connected to BTech, and inshallah after that we will start our module 5. Our module 5, in our module 5 we have to discuss harmonics, harmonic filters, design of harmonic filters, and modern HVDC, introduction to modern HVDC, voltage source controller based HVDC systems, which are called HVDC Lite or HVDC Plus. I will just give a brief introduction to those. And I hope within 2 to 3 lectures we'll be able to complete that module 5, and that will complete our almost 100% syllabus. And hopefully in one of the classes, after we complete the syllabus, if time permits, we will have one comprehensive tutorial class. And I advise you all to go through today's lecture and other lectures and revise your previous concepts. And in case of any difficulty, please feel free to ask me. Thank you.